I'm very, very pleased to be joined by Professor Veena Sahajwalla. Veena, you are somewhere down in Australia. I am somewhere up in the UK, but by the magic of podcastery, we can have a conversation. Although it is your evening, I think, and my morning. But thank you very much for joining us, and welcome to the podcast.
Thank you so much for having me, Alex.
Well, look, we're going to talk about a few things today, not least the work that you're doing in materials research and science around steel and ceramics, and your overall work in reforming and recycling. But before we do that, could you just give a little bit of an overview of, I suppose, your background and what's brought you to this point in time, just to give us some context for the discussion we're going to have?
Yeah, Alex, that's a very good question to start with. I lived the early part of my life. I was born in Mumbai, and for people who know a little bit about Mumbai, it's one of those places in India that's so fascinating. There's industries, there's lots of people, so much going on, and I guess from the context of thinking about how we use our products, how we repair it and keep products, in our lives for a lot longer. That supports local economy and supports the guy down the street who might be fixing your shoes. All of these little things that I grew up seeing in Mumbai, had a big role to play in my life because I think I was really fascinated with how, commerce and basically entrepreneurship and all of this would come together, and it all meant that I guess sustainability and use of products in a way that kept products alive for a lot longer time was already well and truly a concept that was accepted. Now, fair enough, it was because of necessity, and people couldn't necessarily always afford to buy new things all the time. But I just remember, one pair of school shoes in a year, and it had to last the whole year.
Yeah, that's not just unique to Mumbai, is it? I think a lot of us who grew up in well, for me, it was the 70s, as we were saying before this began. That's a culture I remember well. But anyway, interesting background. So now we flash forward to today, and you are a professor of, or the professor of material science at the University of New South Wales. And part of that remit is the oversight of the Smart Centre for Sustainable Materials Research. Can you, again, just give a little bit of context for what that is and the work that you and your group there are doing?
Yeah, so Smart Center, when I founded it more than about a decade ago, was very much about, really challenging the norm that some things were automatically classified as if they were not recyclable. And it was sort of understood that, oh, well, it's too hard to recycle, it's never going to work. But I guess for me, fundamentally, it was actually challenging that notion that, we couldn't recycle some products. So when we first started, it was very much about, yep, we of course need to have fundamental research to basically show that it can be done in our labs, but also at the same time, working and partnering with industries who are excited about the concept that recycling and looking at rather complex products in a whole new light could actually present fantastic new opportunities in the long term. So Smart Center was really set up because we wanted to be able to both do fundamental science and also at the same time look at the translation of that fundamental science into practice and collaborating with our industry partners.
More and more, as me and my team are getting embedded in decarbonisation, I find it really fascinating the partnerships that are forming between academia and the real world, I will say in appalling air quotes, but academia and industry. And there's so many interesting collaborations. And the one, the way that I found my direction to you, if you like, was through an article in the Times about a month ago, I think it was, and it was talking about research, specifically the research you were doing around the use of both coffee grounds, but also recycled tyres to lower the carbon in the manufacturing of, I think it was specifically steel. I know since then you and I have talked, you've explained that ceramics and other materials have a role here, but let's start there because, I mean, honestly, that article pleased me because it was so specific about coffee grounds. That's mad. Can you just give us a little background to how did that come about? How do you find this route in to these interesting combinations of both recyclable materials, but also a process where you can affect such change?
In the world of business, and people talk about vertical integration, and we hear often these terms in business. I guess what I always love to think about in my own headspace, but why can't we think about lateral integration? And when we think about lateral integration, suddenly you can basically say, well, there should be no boundaries between, industries and what might be coming in from one area where waste or end of life products is no longer useful in its current function. And so tires are a good example, right? I mean, when a tire no longer is roadworthy and it's not safe to use it as a tire, it doesn't mean that fundamentally the materials that are in a tire are no longer useful. Physically might not function as a tire in a safe manner, but from a chemical perspective, from a materials perspective, those basic molecules in rubber are still there. So why would we not look at its life in a whole new form? And this is where, of course, the journey for me all those years ago started, where it was very much about challenging the notion that, all you can do with it is, use it for a little civil, road base, or you just have to burn it to get energy. I think it was really about challenging the norm that it's got to be put to really high value manufacturing, and high value manufacturing in a way that also supports the needs of our economy globally. So one of the things, of course, that we've been doing is looking at, well, what are those molecules, and could those molecules actually be put to really good use? And one of the fundamental molecules, of course, that is there as part of the overall structure, and the elements are basically carbon and hydrogen. So the question in my mind was, well, what if you could actually release that as a hydrogen molecule inside an actual manufacturing process? So the ability to have access and isolate and liberate them inside a steelmaking furnace was an obvious question, because to me it was really about saying, well, it's got enough carbon, so it can actually replace coal and coke, the traditional materials that are used in steelmaking. But that bonus presence of hydrogen meant that almost it was that curiosity that said, oh, I wonder if this could actually deliver bigger benefits than traditional coal and coke. And of course, that's again counterintuitive, because you tend to think, well, if I've got waste and I'm using waste in a manufacturing process, oh, surely it's got to be bad. But I think this was where, of course, challenging the norm came in, where, if it's got enough hydrogen in tires, and if you could, as long as you could liberate those molecules inside steelmaking furnaces, why should it be bad? Because here we are all these years later talking about hydrogen. But actually, ironically, when we started all of that work, that was, in a way, why, in my mind, it was all about green steel, because you could then suddenly go, okay, I know I need a certain amount of carbon in the process of making steel, which is there in those tires as well. But I've got this fantastic hydrogen as well. And I guess, this is really where that journey of reform can happen, because now we're looking at using those elements in a completely different way. But in the case of green steel, it was even better, because it was all about liberating that in situ inside the steelmaking furnace. So what that then meant is you were also thinking about how it could be done in a cost-effective manner, but more importantly, could it be done in a way that would be acceptable and good for a steelmaker? Because if I'm a steelmaker, I'm really also wanting to know how this is going to have an impact on my manufacturing process. And this is where the win-win outcome was, that from a steelmaker's perspective, we actually proved that it actually delivered better outcomes than using coal and coke.
That's incredible. So what kind, in terms of the quality of the product that comes out?
It's the actual process itself, because of course, as we're talking about hydrogen, as we're talking about how these, materials, this rubber is actually now transforming, and that transformation allows it to now, instead of being some complex molecule, which is what's there in a rubber product, it's actually more about liberating those small molecules. And these small molecules, which are extremely reactive, they can actually participate in those reactions that a steelmaker needs to see happening inside the steelmaking furnace. Because when you want to produce metal like steel, you need to actually have iron that is basically obtained inside that steelmaking furnace. So the production of that basic metal, iron, and of course, steel is an alloy of iron and carbon and other elements. You want to make sure that I can actually keep producing that. So the efficiency gains came from the fact that the reactions, in fact, were promoted in a far more efficient manner inside that steelmaking furnace. And we've got these fascinating, visuals where inside our own furnaces in our lab, we could actually watch these reactions taking place in front of our very eyes. And I've got to tell you, in the early days, it was a fixation. I had to keep watching these videos over and over again just to look at it and go, oh my goodness, I can't believe what I'm seeing. And this was happening in our labs, of course, in the early days. So I think you can imagine for all of us, myself and of course our researchers, it was one of those things that it gave us goosebumps every time we watched the video.
So that was the lab stage. So you've obviously moved on since then. What phase of research and development are you in at the moment, and what kind of scale of production is possible as of now?
So for us, really, that whole partnership with the steel industry in Australia started, at that time, and we wanted to be able to, of course, show that we can achieve those outcomes in an actual industrial scale furnace, which meant that we needed to collaborate and partner with industry. And long story short, I mean, all credit to Australian manufacturers that here we are not only doing more research in this space, but also having done industrial evaluations and testing on that scale furnace, which of course steelmaking furnaces, electric arc furnace for in this case, is still by no means a small furnace. So to really have that support from steelmaking industry to do all the work, where now we have got evidence that even on a full-blown, actual industrial scale furnace, it delivers those benefits from an efficiency point of view, is something that I'm always going to be grateful for, because I think unless and until we take it up to that industrial scale, we can never say that this is going to work. And also the Australian Research Council, so the ARC that actually funded the research, meant that it's like anything else. You take big risk when you're talking about a brand new blue sky idea, and to be able to have funding, it just goes to show that that's such a critical foundation for research. It's not just about having an idea in your head, but it's about having that resource that you need, just basically being able to do those rather difficult experiments in the lab, but enough confidence in showing that the science works, and really proving that the scientific hypothesis that we had actually started to develop at the time was working. And to me, it was important, that groundwork, that scientific foundation, which then meant that we could actually show to industry in Australia that this was something that can work. And I guess interestingly at the time, what did help slightly is the fact that this research won the Eureka Science Prize here in Australia. So I have to say that certainly does help a lot when when you do win these kinds of science prizes, that industry looks upon that as a really important moment when they can kind of look at scientific research, and to really appreciate the fact that its time has come to take it out of the labs and into an industrial scale.
Today, or this week, or this month, what kind of stage is this at? Are we still in demo phase at a steel plant, or where are you in that cycle of scaling up into eventually what becomes an actual value chain or business model? Where are you now?
So we've got basically an industry partner here in Australia who's looking at different ways in which we can introduce these types of materials into steelmaking. We've got polymer injection technology, so that's coming in through an injection process. And that's something that, because we've been running it on industrial scale furnaces, we've got evidence that shows that green steel does work. And that's really where we're at, where on an industrial setting, we've been able to show that it makes sense commercially as well to do that. And that is why, of course, when the early days, when we started with our industry partner, at the time, it was very much about proving that it makes sense from an operations perspective, but also that it makes sense from a commercial perspective. But even more so, more and more now, of course, as the world has moved further and further into that determination that we're going to be heading towards decarbonization, and we want to find many pathways to reduce our carbon footprint. We've got companies who are supporting us in the research journey, are also looking at, increasing the amount of these types of resources, whether they are tires or plastics, as sources of carbon and hydrogen inside a steelmaking furnace. So that's where we're at. Yes, in an ideal world, we'd love to completely eliminate the need of coal and coke in an electric arc furnace. And I know we'll get there, because I think some of the new research that we've been doing that holds sort of next generation of green steel is really about proving that, a time will come when we'll be able to show that whatever the pathways are for introducing these materials inside the furnace, that it delivers a win-win outcome for the steelmaker as well as for our environment. So I think, to me, the credit to the steelmaker, in this case, Molikov, who's actually been very committed to really supporting that R&D in this way, has been very important.
To what extent are you looking to take this overseas, or does it stay because of the nature of funding? Is it focused entirely in Australia at the moment? Is there any opportunity for international projects? What's your view on that at the moment?
Yeah, absolutely. From our point of view, with our partners, our steelmaking partners, the goal is very much that we want to be able to take the technology out to the world. And indeed, that's where they're being approached by many, many steelmakers to look at the possibility of really taking this technology out to other parts of the world. Because I think, as we are finding, more and more industries are committed to reducing their carbon footprint. And of course, who doesn't have lots and lots of spare waste tires locally available that they could find? So I think for a steelmaker to really access these types of resources like waste tires locally, and that's really an incentive as well, that they can really reduce their carbon footprint by doing recycling, so that alignment of recycling and manufacturing and reducing carbon footprint is really a whole new shift in the mindset. And I always like to think that if you've got steelmakers across the world who are really interested in this kind of work, it just goes to show that for many, many industries, this may well be something that they're thinking about. They probably haven't considered what kind of waste resources might be suitable for their operations, though. But this is where, of course, new research can really shine a light on where our future lies in terms of aligning recycling and reforming with manufacturing.
Yeah, well, that neatly takes us into kind of example two, if you like. So we talked a bit about steel. When you and I first connected, you also mentioned the work that you're doing in the ceramics industry. So let's look at that as a kind of different kind of case example. What has been your route into that? And I'm assuming that's not also the tire recycling model. So what are the materials that you're bringing to bear there? And again, what stage is the research at?
Yes, in that particular case, the two key materials that we're using are waste glass and textiles. And from our point of view, again, it's just really asking this question that, yes, as much as we all need to reduce our consumption of textiles and that throwaway society that we have just become over a period of time, because it was just so cheap and it was just easy to throw it away. But even if you look at where textiles, when they do reach the end of their lives, and garments that then are no longer fit for wear, we shouldn't be just throwing it away into landfill. The fact that at a very basic level, there's still a lot of value in our textiles, whether they are our natural materials or synthetic materials. The ability to actually think about reform where it becomes part of a whole new product. Doesn't have to come back to life as a garment. It can actually come back to life as something else we have in our homes, not our clothes, but our hard ceramics. And of course, again, ceramics is something that, we just take for granted, right? I mean, we've got tiles at home, for example, our floor tiles. And that's a good case in point. Such a, shall we call it, everyday product. We probably never give it a second thought. But yet it's an important part of our lives, whether it's in our homes or in our workplaces. So I think it's, again, asking the question that what if we could manufacture, our basic products, and especially when we want hard wearing products like our tiles, what if we could manufacture that out of waste glass? And what if the color in these products could come from waste textiles? You then have got a solution that almost sort of says, what, this could be done anywhere in the world, because again, we've got plenty of access to broken glass and old clothes. So I think it's also, in a way, that notion of thinking beyond traditional recycling and saying this could well be a whole new form that these materials, and very unlikely combination, you never think about recycling glass and textiles together, because one's a really hard product and the other's beautiful and soft fabrics and materials. So in a way, very unlikely partners coming together to create a whole new functioning product. So the example of green ceramics in there, that journey is very much now that we are at the phase of commercialization. That commercialization journey has been funded through a grant here from New South Wales state government, through the Office of the Chief Scientist and Engineer, with a funding program called Physical Sciences Funding. And that's really been very important for us in that commercialization journey, because you could do all the research in the world, but if you don't actually get it out into the hands of end users and really try it in a real world setting, you don't actually have that evidence to show that it does work outside a lab environment. So yes, you need all the engineering data that you, of course, have to produce. You have to test it in all sorts of different ways. But once you've done that, you have to put it into the hands of end users and get end users to really try it in that real world setting and be convinced. It's not just about the product has got all the right engineering properties, but what about the designers who might want to put it into various settings inside apartments and homes? These designers will look at it from that lens. So it's got to really fulfill the requirements, both from a hardcore engineering point of view, but also aesthetically, it's got to be appealing, because otherwise people are not going to use it in their homes.
I was about to say, so one is a process benefit and the other is a recipe benefit. But of course, the whole point, going back to steel, is that carbon and hydrogen are very much part of the recipe per se. It's not just a process that the steel goes through. It is part of the recipe. So that's interesting. So I have this image in my mind of you having this little band of researchers who each own a material, desperately trying to find a new source for it. Is that how it works? Or how does that, what's the origin of some of the ideas? Because they're not all, I don't think I'm crazy for saying this, they're not all immediately apparent. So how does that process of the very early stage identification of a possibility work?
Yeah, I guess it suffices to say that it starts at the rubbish bin at our home, where there's a constant battle where I think my husband, who's a clean freak, is trying to kind of tidy up and, throw it away. And I'm constantly going and retrieving that out of the rubbish bin. And so therefore we've created a little sort of area at our home where once something is retrieved out of the rubbish bin, and once I'm sort of looking at it going, oh, no, this is too good to be, for us to be throwing it away. It actually has a place, a special place in our home. So suffices to say that's where it all starts. And of course, as you can imagine, once you have a place like that, there's no shortage of products that keep kind of resurfacing. So whether it's food packaging, or whether it's indeed a broken piece of I guess an electronic device, they all land up on that little table at home. But I guess it's interesting, isn't it, that it's almost one of those things where once we all feel really strongly about something, it's that both the head and the heart that then come together. Then to actually then bring that in a way, in that context, in a laboratory setting, is a whole nother challenge. So it is a challenge where you can kind of go, okay, let's sit down, we all sort of come together, and then someone might go, okay, cool, I think we need to go back and just understand and analyze the properties of this fabric or this glass. And there might be someone who's already studying ceramics, and they might go off and analyze those properties. And then someone who might look at this fabric and go and analyze that. And so it's very much about that creativity that comes from all of us getting together. And it's such an exciting moment, because it can be one of those things where the conversations just sparked off by the fact that we're all challenging each other. But at the end, we all also recognize that unless and until we can then show that we've made a prototype in our own microfactories, we can't see it for real. So that sort of next stage of, even in our own microfactory, to create something that is viable, is the point when we all get super excited.
Having brought you right back to the origins of some of these processes, let's flip to the point at which you're starting to work with industrials. And I'm just wondering what you've learnt from that experience, because clearly that point at which you bring in an industrial partner is a bit of that must be a total switch of headspace, because the kind of the energy or the interest or the expectation has to shift a little, because the partner wants something different as an outcome. So what have you learnt or observed from that process, both on how you and your group need to work, but also what are you learning about the industrials from that?
When it comes to interacting with industry, we always have to respect the fact that they're running a business. And for them, that's always going to be the primary focus. As much as they love the research and the science and get excited about new ideas, then I have to say, they all get really excited about, every time we have our meetings and discussions about what could this lead to, that questioning. So even if we've got all kinds of new scientific ideas, very supportive at an industrial scale to think, okay, well, this could be that, or that's what we could be doing. But there's also always that practical sort of question associated with it. So even before we start to talk about, is this going to become a commercial reality, we then have to think about, okay, let's all work together in terms of thinking about practically how we would deliver that, right? Because it's one thing to do it in a laboratory setting with our small furnaces and our small modules. But then when you're actually starting to take it out into an industrial setting, it's about knowing that you can deliver it and do it on that scale at which they want to operate. So, if you were looking at replacing, coal and coke in an electric arc furnace steelmaking process, you would want to know, how am I going to meet those requirements in terms of the material and the job it has to do. So not just the physical delivery of the material and what it's going to look like, but once it gets inside the furnace, does it actually do the job that it's meant to do? So it's all of these questions that, of course, you need science for that, but you also need to know that in a real world furnace, there are many other complicated things going on. And your lab furnace is almost a nice, simple, isolated zone in which you can study that reaction in a lot of detail. But when you're talking about a larger scale furnace, there are so many other phenomena, competing phenomena, that are going on. And so it's also exciting in a way, challenging, yet exciting, to think that, oh, I wonder if this is going to kind of do this, or is it going to go down the path that I think it will? So there's also those questions that kind of literally pull you apart in many different directions. And I guess in a way, it's that scientific sort of thought experiment that happens in your head, because you've gone from perhaps a little tiny baby furnace into a larger furnace. And I guess in my head, it's always that visual. It's almost like sometimes I get up from a dream and I go, oh my gosh, that was a pretty scary dream, because you also think about all the things that could go wrong. And so yes, it's always going to be that constant, I guess, journey of understanding how do you deliver it, you know, at that another scale that takes it out of the lab into a real world setting.
Yeah, and all the implications as well beyond the furnace or whatever that kind of central component is, the implications for supply chain and business models and partners. Is that, do you get involved in that stage or in that kind of part of the thinking around this, or do you tend to sort of focus more on the materials science, pure and simple? How far does your influence and interest, I suppose, extend down that value chain?
The commerce side of it is always going to be something that industry is a lot better than we can ever be. They know their business, they know, how to deliver something in an economically viable manner, and really understanding the supply chains of materials. So we actually learn so much, and we give a lot of credit to our industry partners where they give us that guidance, and we talk about those things. And of course, that's always of interest to me, but I think, we don't have that full knowledge, and industry partners are absolutely the experts when it comes to understanding the commercial feasibility of an idea. And so part of that excitement for us and our team of scientists and engineers is always to learn from our industry partners and to understand how could we help and do things that might make an idea, commercially attractive for our industry partners. So I'm not saying we have all the answers on day one, but I think that's, again, part and parcel of the journey, and it's a learning journey. But that's exactly why it's a collaboration. It's a partnership, that as much as, we might understand our science, they also have to be mindful of running a business and understanding the commercial feasibility. So I think this is where the partnership of science and business, and the two working together, is basically the recipe that we need to bring innovation and new ideas to become ultimately commercially viable.
If we sort of step back from the specific research that you're involved in, I think you're kind of, when I look at you and the work of the materials science group and the Smart Centre, really it's about that, an interest in those hard and hardest to recycle materials, right? I mean, if we're going to reduce it to the simplest statement, it's about how can we make use of these hard to recycle materials. And I know, again, in our prep chat for this conversation, you talked about something which I've not really heard about or thought about in my kind of process of thinking about decarbonisation, which is kind of quite a strategic idea of decentralization of manufacturing, and how that might open up more opportunities for real decarbonisation in all kinds of situations around the world. Now, I probably just explained that appallingly because, again, it was a new idea to me. But can you just tell us a little bit about like this idea of decentralization, and why does it matter in the context of carbon abatement, decarbonisation, and those sorts of themes?
When we think about, manufacturing and making materials, whether it's metals or any of the other things and things that we use in our homes, I mean, we've talked about green ceramics, the tiles. I think in all of these cases, really sort of asking the question, if a product had to travel, shorter distances, to get to the end user, and equally, if the raw materials had to travel shorter distances to get to the factory, you then have already reduced, that transport mileage. And by reducing transport, you've already now started to bring down the carbon footprint. But asking the question, that is it really possible that we can imagine a situation where decentralization and the ability to manufacture high quality products could be done on a scale that is right for that particular purpose. So in this case, if we're saying that, look, the purpose is really not to capture a global market, but if the purpose is really to capture a regional market, and you can almost imagine a situation where in that regional setting, there's more than enough waste resources that can be fed into that regional manufacturing solution, then that regional manufacturing solution doesn't need to be a mega factory. In fact, this is exactly why we've turned it upside down on its head. And we're saying, no, actually, it makes sense if it is a micro factory, because then your investment is a lot smaller. You're now looking at raw materials, which are coming from waste, not coming over long distances, but rather coming over relatively shorter distances. The product is manufactured on a scale that is right for purpose. So here we are talking about not economies of scale, but we're talking about economies of purpose, because of course your market could also be regional. So the idea that you can actually create this whole new way of doing manufacturing hinges upon the fact that as long as you can make high quality products that is fit for purpose and that end users will be able to use it because it does the job it's meant to do. So if you're making a floor tile out of waste materials like glass and textile, and this green ceramic has got all the right engineering properties, and of course people who are in your regional areas are actually excited about the possibility of using recycled products, it means that you can actually achieve that notion of what, a decentralized manufacturing solution could look like in the future, because we will always be generating waste resources, whether they are glass or tires or textiles. So we don't want to be taking these waste resources over long distances. And the other side of the picture is that we'll always be using, tiles and materials in our homes. So if we were actually looking at, local production and supporting local economies, you've suddenly achieved both a reduction in the carbon footprint, but you've also enabled local economies to flourish. So in a way, if you can achieve both of those, you can actually do it by thinking about microfactories and a decentralized way of manufacturing.
Yeah, I think that there's so many important points in that. When you think about all of these pieces of work that you have ongoing at the moment, what are you most excited about next, and what do you see happening in the kind of short term? What's next on the horizon for you and also for the teams you're working with?
There are, of course, so many things that I'd love to be able to do,
And a huge pile of rubbish that you're still sorting through.
Exactly right, exactly right. But I guess again, if you think about where the needs of the world are going to come from, and of course we've talked about decentralization, but when we think about how we're going to actually have energy and storing energy and batteries, I think from our point of view, that whole question of if this is going to become the way of the future, then thinking about the materials that go into making these types of products like our batteries is an important question, because for us, again, a lot of those materials and those resources are limited on our planet. And so when we are talking about the kinds of metals and rare earths that go into making these kinds of energy storage devices, when we talk about renewable energy, we need to think about where fundamentally all the materials that go into making the products. And that's why when I bring to forefront the question around energy, it's about saying that the materials that go into making these devices are also to be seen in a way as renewable materials. So starting to bring that thinking into bear, that just because your battery might evolve over time, and so it should, there's a lot of research that is actually going to make sure that these devices, these energy storage devices are going to be more and more efficient over time. But again, it's fundamentally that those materials that are embedded inside our batteries, for example, can actually be harnessed over and over again if we can find a way to manufacture and remanufacture those materials into a new form. And for us, the most exciting thing about that is that we know that the world is facing those challenges. So again, it's one of those things that it is a global challenge, but yet again, interestingly, a regional solution would make a lot of sense, because again, we all have got batteries that, for example, we're thinking about batteries that are disposable in nature. How would you just throw it away? Or would you actually say, okay, well, it's come to the end of its functioning life, but you know what, if we can unpack those materials and bring it back to life in new forms, that would actually make it's so possible to imagine a future where on one hand we've got renewable energy, and then on the other hand we've got renewable materials, because fundamentally that's what we're talking about here. Materials that can be renewed in different forms. And the reason why I'm talking about this particular program is we've just started, and through funding of the Australian Research Council, a whole new research hub that is called microrecycling. And this microrecycling is very much about, addressing the rather difficult and hard problems. And the reason why I picked up on something like batteries is we know how difficult it is. And so from that point of view, it's really basically saying, look, we've got to start asking the difficult questions. We've got to start saying that if we ask those questions, and if we can, understand the science, and in this case, we literally had to develop a whole new word. So micro-recycling was a word that, I had to come up with, because I think in a way it captures that point that we can't just think about recycling on that larger scale. And at the micro level, there is still a lot of value in our materials, as long as we can find a way to do that micro recycling. And once we can unpack that and we can understand that science, then that can go a long, long way in showing that even the most complex products can actually be brought to life in many different forms. So I want to give credit to basically the Australian Research Council, which is the funding agency, and our industry partners. I've mentioned people like Molycop and TES, and indeed so many industries that support us on this journey, because this kind of collaboration that we've talked about between government and industry and research is so critical to make sure that we can deliver genuinely a collective future that shows that it is possible to decarbonize, it is possible to deliver new jobs and deliver a better planet for our future.
Well, that's a great note to finish on. And just from my perspective, Veena, thank you very much for a really interesting conversation, but also one that's so rooted in possibility and opportunity rather than being rooted in problem, liability and risk. It's just a very refreshing way of looking at the work that needs to be done. So thank you very much for joining me.
Thank you so much for having me, Alex.